Various theories were proposed to explain the behavior of the coordination complexes. Among them, Werner's theory, valence bond theory, crystal field theory, ligand field theory, molecular orbital theory are some of the theories which helpful in explaining the behavior of the coordination complexes. Today let us study valence bond theory. Valence bond theory satisfactorily explains the structure and magnetic properties of large number of coordination compounds. This theory was proposed by Linus Pauling. Let us study some of the salient features of valence bond theory. First point, the central metal atom or ion has the required number of vacant orbitals. These vacant orbitals are accommodating the electrons donated by the ligands. The number of vacant orbital is equal to the coordination number of the metal ion for a particular complex. Let us study the theory in detail with the help of an example. The metal ion which is undergoing the complex formation is cobalt 3 plus ion. Cobalt 3 plus ion consists of 3d8 electrons in its valence shell. See, the coordination number of cobalt 3 plus ion is 4. That's why the valence orbital, that is 4s orbital and 4b orbitals, are the vacant outermost orbitals of this cobalt 3 plus. So there are 4 vacant orbitals are available in the valence energy level of cobalt 3 plus ion. The next feature is the vacant orbital of the metal ion or atom undergoes suitable hybridization to yield a set of equivalent hybrid orbitals of definite geometry. Here there is one 4s orbital and 3 4p orbitals are there. These 4s orbital and 4p orbital undergoes a mixing process. That process of mixing orbital is called as what? Hybridization. So as a result of this hybridization, we get 4 sp3 hybridized orbital, which is equivalent to the coordination number of the cobalt 3 plus ion. This is the structure of sp3 hybridized orbital. See, the geometry or the shape of the complex depends upon two factors. One is coordination number and the second one is hybridization of the metal atom or ion. See, if the coordination number is 6 means the geometry of the complex is octahedral. If the coordination number is 4 means the geometry of the complex compound may be tetrahedral, square planar. The octahedral complexes having coordination number 6 and they may undergo sp3d2 hybridization or d2 sp3 hybridization. If the coordination number is 4 means the hybridization in tetrahedral complex is sp3 hybridization. If the coordination number is 4 in the square planar complex, the hybridization is dsp2 hybridization. If the coordination number is 5 means that complex is trigonal bipyramidal, is the hybridization is sp3d hybridization. So the third feature of the valence bond theory is a ligand orbital containing a lone pair of electron forms a coordinate covalent bond by overlapping with the hybrid orbitals of the metal ion. See, metal ion, already I told you the second feature, metal ion undergo hybridization. Now the ligand orbital overlap with the metal ion and forms a coordinate covalent bond, okay, or a dative bond. Next feature is the magnetic moment of the complex can be used to determine its geometry. See, first I told you the coordination number is used to determine the geometry. The next one is the magnetic moment also can be used to determine the geometry of the coordination complexes. See, the magnetic moment is determined with the help of Gauss balance, GOUI-BALANCE, Gauss balance. So you can see the image of the Gauss balance. In between the two bar magnets, the coordination compound, a sample of coordination compound is placed. Based on the magnetic moment, the shape of the coordination complex or the geometry of the coordination complex can be determined. Fifth salient feature of VB theory is in the formation of complex. If the metal utilizes its inner d orbitals, then such a complex is called as inner orbital complex or low spin complex or spin paired complex. On the other hand, if the metal utilizes its outer d orbitals for the complex formation, then such complex is called as outer orbital complex or high spin complex or spin free complex. Example for the inner orbital complex or low spin complex. So in the metal atom or metal ion, the vacant orbital is 3d orbital, means the ligand, the incoming ligands donates the electron the 3d orbital. So this complex formed is called as what? Low spin complex or spin paired complex. If the metal atom utilizes the outer d orbital, that is 4d orbital, for the complex formation, so such complexes are called as what? Outer orbital complex or high spin or spin free complexes. For example, a diamagnetic complex, that is hexamine cobalt 3 chloride, is taken. You can see the sample in the module. The electronic configuration of cobalt atom is argon 3d7 4s2. See, the distribution of electron is given in this. Oxidation state of cobalt in hexamine cobalt 3 chloride is plus 3. Electronic configuration of cobalt 3 plus ion can be represented like this: argon 3d6 4s0. See the difference in the electronic configuration between cobalt atom as well as cobalt 3 plus ion. In this 3d orbital, there are 7 electrons are found in the cobalt atom, whereas in cobalt 3 plus ion, there are 6 electrons are found in the 3d orbital. So we could see more number of, that is 4 unpaired electrons in cobalt 3 plus ion, right? So the magnetic nature of this complex hexamine cobalt 3 chloride is paramagnetic due to the presence of 4 unpaired electrons. But the magnetic studies have revealed that hexamine cobalt 3 chloride is diamagnetic in nature. Why? Because 2 vacant 3d orbitals are made available for hybridization. See, the 3d orbital, the last 2 vacant orbital and the 4s orbital, there is one 4s orbital and there are 3 4p orbitals. So 2 d orbital, 3d orbital and 1 4s orbital, 3 4p orbital undergoes hybridization, and this hybridization is d2sp3 hybridization, and we get 6 equivalent d2sp3 hybridized orbital. Now the 6 d2sp3 hybridized orbital accepts 6 lone pairs of electrons or accommodates 6 lone pairs of electron, which is being contributed by 6 ammonium molecule and form a coordination complex like this. That's why hexamine cobalt 3 chloride is diamagnetic in nature. So in this complex, there is no unpaired electron. We can see all these electrons are paired up. That's why this complex exhibits diamagnetic property. The geometry of this complex is octahedral. See, hexamine cobalt 3 chloride forms low spin complex or spin paired complex because the inner orbital involves in the hybridization. Let us see few more examples. Hexamine manganese 3 plus. So the electronic configuration of manganese atom, argon 3d5 4s2. You could see in this 3d5 configuration, all these electrons in the 3d5 orbitals are half filled. 4s is completely filled. The electronic configuration of Mn3 plus ion. So 3 electrons from this manganese atom is lost. Now argon 3d4 4s0. Here there is one 3 vacant 3d orbital and there is one 4s vacant orbital. To accommodate 6 lone pairs of electron, in manganese there are only 2 vacant orbitals are available. So 4p orbital is also an empty orbital that accommodates the electron which is donated by this amine group, 6 amine group. So the 4 unpaired electron which are found in the Mn3 plus ion are forced to pair up. So 2 empty d orbitals and 1 s orbital and 3 p orbital undergo d2 sp3 hybridization. It is diamagnetic. This complex is called as what? Inner orbital complex. Same way in hexacyanidoferrate also we can find hexacyanoferrate 2 ion. Atomic ion has argon 3d6 4s2 configuration. The Fe2 plus ion's electronic configuration is given like this: argon 3d6 4s0. Here s orbital is vacant. To accommodate 6 pairs of electron in ion, this unpaired electron which is found in the Fe2 plus is forced to pair up to give 6 and pair up to give 3 d6 electronic configuration, and the d2 sp3 hybridization is also taken place. So this complex is called as what? Inner orbital complex. Sodium hexafluoridocobaltate 3. Electronic configuration of cobalt is argon 3d7 4s2. So the valence orbital consists of 3d7 4s2. So in the 3d7 orbital there are 3 unpaired electrons can be seen. So the oxidation state of cobalt in hexafluoridocobalt is 3 plus. So the electronic configuration of cobalt 3 plus is argon 3d6 4s0. You can see in this 3 plus cobalt 3 plus ion there are 4 unpaired electrons, whereas in cobalt atom there are 3 unpaired electrons. Magnetic studies reveal that sodium hexafluoridocobaltate is paramagnetic in nature. Why? Because the vacant 4s orbital and 4p orbital and 4d2 orbitals are undergoing hybridization. So to give sp3d2 hybridization, so we get 6 equivalent orbitals equal in their energies. These sp3d2 orbitals accommodate 6 lone pairs of electrons which is contributed by fluoride radical, and this complex is called as what? Outer orbital complex or high spin complex or spin free complex. Let us study few more outer orbital complex. Hexachlorido manganate 3. Manganese in its atomic state. Argon 3d5 4s2 configuration. So hexachlorido manganate 3 minus. So 3 electrons are lost from this valence shell of a manganese ion. So the electronic configuration is given like this: manganese 3 plus ion has argon 3d4 4s0 configuration. This valence orbitals undergo hybridization. After hybridization there are 1 4s orbital and 3 4p orbital and 3 4p orbital and 2 4d orbital undergo hybridization. So it is an outer orbital complex or outer orbital paramagnetic complex. Why? Because all these 4 electrons are unpaired. Likewise in the next complex, hexafluoridoferrate 3. See iron in its atomic state, argon 3d6 4s2 electronic configuration. In the complex state, iron forms Fe3 plus ion. So the electronic configuration is argon 3d5 4s0. Through 3 electrons are lost, okay, and forms Fe3 plus ion. Now we get the valence shell 4s orbital, 1 4s orbital and 3 4p orbital and 2 4d orbital undergoes hybridization to form sp3d2 hybridization. Both the complex we could see sp3d2 hybridization. So all these orbitals are singly occupied and paired electrons are there. So it is a paramagnetic outer orbital complex. So in the case of octahedral complexes formed by metal ions such as titanium 3 plus, vanadium 3 plus and chromium 3 plus. In titanium 3 plus, we can see the valence electronic configuration argon 3d1 4s0. Argon 3d1 4s0. So here only one unpaired electron is found in the titanium 3 plus ion. The shape of this complex is octahedral. Same way vanadium 3 plus, and the valence orbital of vanadium 3 plus consists of argon 3d2 electrons. There are two unpaired electrons are found in the valence orbital. The shape is octahedral. Next, chromium 3 plus. See, in chromium 3 plus, argon 3d3 4s0 electronic configuration. So there are three unpaired electrons are found in the valence shell. So the magnetic behavior of these free metal ions and their coordination entities are similar. Hence, these octahedral complexes are always paramagnetic in nature. They may ask question like this: why titanium 3 plus, vanadium 3 plus and chromium 3 plus are paramagnetic in nature? Because of the number of unpaired electrons found in this 3 plus complexes. They behave like a paramagnetic substance. So let us study number of orbitals and the type of hybridization. If the coordination number is 4 means the type of hybridization sp3. The distribution of hybrid orbital in space is tetrahedral. The coordination number is 4 means it can also forms dsp2 hybridization and this complex shape is square planar. If the coordination number is 5 means sp3d hybridization trigonal bipyramidal. If the coordination number is 6 means sp3d2 hybridization octahedral. If the coordination number is 6 means sp3 d2 sp3 hybridization, there is coordination geometry shape is octahedral. Let us study the structure of potassium tetrachloridonickelate. It's a paramagnetic tetrahedral complex whose coordination number is 4. So the electronic configuration of nickel 2 plus ion is argon 3d8 4s0. See, it may undergo, it is a paramagnetic complex. It may undergo sp3 hybridization and dsp2 hybridization. But actually this complex, this metal ion undergo sp3 hybridization. It doesn't involve in the dsp2 hybridization. Why? We can assume for, look at this, there are 4 sp3 hybrid orbitals are there. They can accommodate 4 pairs of electron which is donated by 4 fluoride radical. So the shape or the geometry is tetrahedral in shape. The next complex what we are going to study in detail is tetracarbonyl nickel 0. It's a diamagnetic tetrahedral complex. The electronic configuration of the oxidation state of nickel here is 0. Why? Because carbonyl is a neutral ligand. Electronic configuration of nickel atom is 3d8 4s2. So, the experimental studies suggest that tetracarbonyl nickel is a diamagnetic in nature. See, actually, in the atomic state, nickel has two unpaired electrons. We may expect for a paramagnetic nature, but experimental study says it is a diamagnetic substance. Okay. See, this complex undergo sp3 hybridization. So in the s orbital there are two electrons are found. Now these two electrons are occupying in the 3d orbital. That's why all these electrons are paired up. That's why it exhibits a diamagnetic nature. Now this four carbonyl groups donates lone pair of electron in sp3 orbital and forms complex. So it is a diamagnetic tetrahedral complex. The shape is square planar. All these four carbonyl ligands occupying the four corners of this square planar tetracyanonickelate. So oxidation state of nickel in this complex is 2 plus. Electronic configuration is argon 3d8 4s0. So there are 8 electrons in the d orbital. There is no electron in the s orbital. For this nickel 2 plus ion, magnetic studies suggest that tetracyanidonickelate is a diamagnetic complex. Why? Because these two unpaired electrons are forced to pair up by the strong field ligand called cyanide. So this metal ion undergoes dsp2 hybridization. There are 4 dsp2 hybridized orbital, and this 4 pairs of electron from the cyanide is donated to this dsp2 orbital. The shape of this complex or the geometry of this complex is square planar. Shortcomings of valence bond theory. Although this valence bond theory successfully explains the formation, geometry and magnetic behavior of coordination compounds, it suffers from certain drawbacks. See, all these coordination compounds are generally colored, but the valence bond theory does not explain the color exhibited by these complexes. This theory does not provide a quantitative interpretation of the stability of the complex. It does not give the quantitative interpretation of magnetic data. It fails to predict the exact geometry of complex with coordination number 4. For example, according to valence bond theory, tetramine copper 2 plus is tetrahedral, but according to X-ray analysis, tetramine copper 2 plus is square planar. So these are some of the drawbacks or shortcomings of VB theory.